Welcome to a lesson with Dr. Powell. Let's talk about some vectors that come up as we discuss motion along a curve in 3 dimensions. So right here, we have a curve. And moving along the curve, we have these vectors. Now notice how this frame of reference is kind of twisting. We can kind of look at it from different viewpoints. You see the blue vector that's going along right here. It stays the same length the whole entire time. And so do the other vectors in this particular example. The blue arrow we call the t, or the unit tangent vector. That's the blue vector. So that's the blue unit tangent vector. So notice how it's tangent to the curve as it goes along. And we can actually compute that just by taking the velocity vector itself. So if this curve is represented by a function r of t, then if we take the derivative of that, in fact, we could even notate that with the vector symbol. We take the derivative and we get velocity. And then we divide that by the length of the velocity curve. That's the unit tangent vector. And notice it stays the same length and it just keeps on going. It's always a unit length of 1. Now notice the red vector. Let's take a look at that right now. So if we take a look at what's happening with the red vector right here, notice how it's always perpendicular to the blue one. If we take the derivative of this blue vector, that stays the same length the whole time. The derivative of a vector that stays the same length and doesn't change is always orthogonal. And so the red one actually is that derivative normalized to become a unit. So in other words, the red vector, and we can pause this animation for a minute. The red vector is, so the red we'll give it a name n. It's a unit normal vector, we'll say. So it's red, and we can obtain it just simply by taking the derivative of the unit tangent vector with respect to t, and then normalizing it by dividing by its length. So that's another way of saying what n is right there. So n is this vector. Okay, and it's going to be orthogonal. And let's see what else we have. Let's look at the animation again. And we notice we have this is actually brown. Maybe it's hard to see that it's brown, but the other vector right here, it's perpendicular to both of them. What is that? Well, if you notice, if you take blue and you take red and you think of a cross product, blue cross red, kind of thinking about this, and I'll use let's notate this. We think about just momentarily as the blues being like X, and this being like, let's see, X and Y. Then if we were to turn this, so X actually comes over here and Y would be put over there, and this would be facing straight up, which means that this vector cross this one is actually the brown one. So in our picture, that's what we're describing, this brown vector. So this vector right here is n. This vector right here, or not n, sorry, excuse me. This vector is t. This vector right here is n. And this vector right here is actually t cross n. We give that vector a name and we call it b. Now you see this green vector right here. This green vector is actually equal to the derivative of the vector b, which is the cross product of t and n, and it's a function of t. It depends on t because t depends on little t and n depends on little t, and so b will also depend on little t being the cross product of the two. So this green vector is actually the derivative of b, but with respect not to t, but with respect to arc length or along the curve. But you could rewrite this as db dt dot ds. Let's see here, dt, sorry, dt ds. And you could think of this as taking the reciprocal of this and dividing by it. You would actually notice that db ds is equal to db dt divided by ds dt. Now ds dt is kind of like the speed along here at the curve, which is actually equal to the absolute value of the velocity vector. It's just this is just a scalar, and it's actually that absolute value. So in some sense, you could just say, take the b vector, take its derivative, and then divide it by the absolute value of v, like that. And that's kind of what we're looking at. So this is a vector, and that's that green vector. So it's representing the change of this b here, which kind of represents tilt, kind of like this is like the plane that this curve is in, and kind of this plane is kind of tilting as we move along. It's like going this way or whatnot. In fact, the derivative tells us how this plane is tilting. The plane that has t and n, it's always tilting this way. In fact, why don't we take a look at this and run this again. Let's run this again and see how it tilts. You see how this is twisting? It's twisting around as it goes. So this whole frame is twisting, and that's what that green arrow shows. It shows the twisting, kind of like that's how it's going to be changing. It's the derivative of how it's changing, and the derivative is a vector itself, representing kind of per unit length along the curve, how much this vector b is going to change. The vector b is often called a binormal vector. That's we use b, so binormal. It comes from the t and the n, and you cross them together to get the binormal, and the green is showing how it's changing. Okay, let's look at one more example here in this video before we end. So let's take a look at this. Let's just pause this one. Let's see, pause it. And then let's scroll up here. And we're going to take a look at another one down here. All right, this one right here. Let's take a look at this. So if we look at this particular example, notice that the green arrow gets smaller and smaller. First it's big, a lot of twists, then all of a sudden there's no twist. It's about constant at the end over here. It's about it's pretty constant in this particular example. So the green arrow actually tells you a lot about how the path is twisting as it moves along. And so I hope you enjoyed this little description of the vectors that we have of t, n, b, and we even talked a little bit about the derivative of b with respect to arc length, which is the green vector that you're seeing. And perhaps this is a good time to mention this. Torsion. Torsion is a measure of twisting. It's actually the dot product of the green vector, and it's actually the negative of the dot product of the green vector and the red one that's pointing in. And since the red one that's pointing in, which is the n vector, is a unit vector, dot product is projection. So it's actually the projection of the green onto the red. And so it kind of actually onto the negative of the red. So actually torsion's positive in this example the whole time. Positive torsion because it's projecting onto the negative of n in a positive way. And so we have this nice, so we have positive torsion. At first the torsion is great because the projection is larger, then the projection gets to zero, so meaning less twist. So torsion is a measure of twisting, if we just think of it as being that dot product between the green and the negative of the red. Thanks for watching.